All right, so in the last section, we talked about the mole and Avogadro's number. Okay, and we found out that in 1 mole of anything, we have 6.02 times 10 to the 23rd objects of that, so atoms or molecules in the case of chemistry. But you'll quickly find out, and you guys at home don't really have a full appreciation for this, but it's really hard to count out, 6.02 times 10 to the 23rd atoms. It'll take you a little while. So, talking about and discussing atoms and molecules is not as convenient for us as one would think. Okay, so instead, we're going to start using the mole, or the concept of the mole, in terms of molar mass. So instead of looking at atoms and molecules, we're going to start looking at masses. Okay, a lot easier to count out because then you can just pile your substance on your balance in order to get the mass of it. So we want to talk about molar mass, which is section 6.5. So let's define it. When we had atoms or molecules, basically we were looking at 1 mole, how many atoms were in 1 mole, or how many molecules were in 1 mole. For molar mass, we're looking at the mass of 1 mole of a compound or of anything. Now, molar mass is what I'm going to call it. This concept has gone by a number of different ways, and some of these different vocabulary words have specific definitions of why they're different. But for us in this class, and usually for basic chemistry, the differences between the different vocabulary makes no difference. We still treat the numbers the same, we still calculate the same, they still derive from the same numbers. Basically you can think of all of these next things as synonymous, okay, meaning they mean all the same thing. So a lot of times instead of mass, it's usually incorrectly referred to as weight. So sometimes basically we have AKA, also known as, you can have molar weight. We like the term mass better in chemistry, but weight is used a lot. Sometimes, because we're going to deal with covalent compounds, we deal with molecules. So you might see this looked at as molecular mass or molecular weight. Or when it comes to ionic compounds, they're usually called, it's formula mass or formula weight. Basically, all of these terms are all the same. Okay, we can treat them as if there's no difference between that language. Now, for elements, how we get the molar mass is that their average atomic mass which we first talked about in chapter 3, that is equal to its molar mass. Okay, so in chapter 3, we talked about average atomic mass. So if we were looking at, say, carbon, and we looked on the periodic table, carbon looks something like this, and we said the average atomic mass of carbon was 12.01 AMU. Remember our atomic mass units. Now, because AMU those units don't help us out, we're going to put that in terms of molar mass. So we have 12.01 grams per mole. And what that means, remember when we have these two units here, so unit per unit, remember that lower unit means that it's per one of that. So what this means is that we're going to have 12.01 grams of carbon in every 1 mole of carbon. Basically what we have here is we have a conversion factor. Yay, another one. Okay. So molar mass allows us to convert between grams and moles. This is a very key calculation for us. So let's look at an example. Let's look at how many moles of carbon are in 10.0 grams of carbon. So basically we're given our 10.0 grams of carbon, and we want to know how many moles of carbon that is. In order to do that conversion, we're going to use our molar mass. So we set up a conversion factor here. We have 10 grams of carbon. We want to convert from grams of carbon to moles of carbon. So we put grams down in the denominator so that these cancel out. We put moles of carbon up top. And remember our conversion factor, okay, or you can remember the definition is the mass of 1 mole of anything. So our 1 goes with our mole. Okay, molar mass is always per 1 mole no matter what. Then our value that we have here, our 12.01 for our mass, goes with our grams. We have 10.0 divided by 12.01 is 0.832639. And we had 3 sig figs to start with, so I'm going to round it off to 3 sig figs, so I have 0.833. I'm going to have to round that 2 up because there's a 6 next to it. So again, saying that again, my calculator gave me 0.8326, okay, and that was moles of carbon. I need 3 sig figs because that's what I started with. So my 8, 3, and 2 are significant. I have to round up because I have a 6 next to my 2. So my final answer is 0.833 moles of carbon. All right. What if I wanted to know how many atoms of carbon are in 10 grams? In this case, now we're still going to involve our molar mass, okay? And we're going to do this same step that we did here, okay? We're still going to, start with our 10.0 grams of carbon, convert that to moles of carbon. And whenever we're involving atoms or molecules, we have to involve Avogadro's number. So we'll go from moles of carbons to atoms of carbon. Okay, so we're looking at molar mass for our first step and Avogadro's number for our second step. So we have 10.0 grams of carbon. Yes, you can just take this answer and convert it, but I'm showing you all in one step here. So we go from grams of carbon to moles of carbon. We have 1 mole per every 12.01 grams. Our final step, we want moles of carbon to atoms of carbon. We have moles of carbon up top, so we need moles of carbon in the bottom. And we want to go to atoms of carbon up top. And Avogadro's number, how we use it, we have 1 mole is 6.02 times 10 to the 23rd. So I still have my answer from the first one here, so I'm just going to go ahead and take that and multiply by 6.02 times 10 to the 23rd. And I get 5.01 times 10 to the 23rd. All right. So that was kind of talking about elements. So we are looking at elements, how to calculate their molar mass. Okay. Elements are exciting, but much more exciting for us is talking about compounds. So let's talk about molar mass in terms of compounds. Basically what we're going to do here is we're going to sum all of the individual molar masses for all of the atoms that we have in the compound. So if we look at the molar mass of KClO3, basically what we want to do is we're going to look at the individual molar mass of 1 potassium atom, 1 chlorine atom, and 3 oxygens, okay, a mole of each of those, and then we'll add those all together. Okay. So what I like to do is just kind of make a list. So we have K, Cl, and O. We have 1 potassium, 1 chlorine, and 3 oxygens. And we want to multiply that by the molar mass of each of those individual elements. So I'm going to flip to a periodic table here. Maybe I'll use a bigger one so I don't have to zoom in. So potassium here, okay, we have 39.0983. You know, 2 decimal places is probably going to be good enough for us. So I'm just going to use 39.10, okay, for potassium. Chlorine is over on the right-hand side. And we'll use 35.45 for that one. And oxygen, this is actually an outdated periodic table here. Oxygen is actually 16.00. So potassium was 39.10, chlorine 35.45, and oxygen 16.00. So we have 39.10, 35.45, and these are all units of grams per mole. And 3 times 16 is 48.00 grams per mole. We add these together. Let's see, we have 0.55 as our decimal there. 9 plus 5 is what? 14 plus 8 is 22. So 2, and carry my 2. I have 3, 6, 10 plus my 2. So I have 12. So the molar mass of KClO3 is 122.55 grams per mole. And this is the molar mass of KClO3. And again, usually you're going to want to keep about 2 decimal places in your molar masses. Okay, you don't want your sig figs to be determined by your molar mass. So the more decimals you can keep, the better off your answer is. Now that doesn't mean you need, 4 or 5 decimals. 2 will usually get you where you want to go. So let's try another example. Let me get a new sheet of paper here. Let's look at the molar mass of saccharin. One of your substitute sugars. Again, don't expect you to know that formula, but I will let you know it's C7H5NO3S. That's a big one. Go ahead and try that on your own. So pause the video, and then I will have your solutions when you come back. All right, so we have carbon, we have hydrogen, nitrogen, oxygen, and sulfur. And we're using our subscripts for how many of each atom we have. So we have 7 carbons, 5 hydrogens, 1 nitrogen, 3 oxygens, and 1 sulfur. And again, you want to look up the molar masses of each of these elements. Okay, carbon is 12.01 grams per mole. Hydrogen, I usually take to be 1.008 grams per mole. Nitrogen is 14.01. Oxygen 16.00. And sulfur is 32.06. So 7 times 12.01. 7 times 12 is 84. Then we have 0.07. Hydrogen, we have 5.04. Nitrogen, we're just taking 1 times that. 3 times 16, 48.00. Sulfur, we stay the same. I could do that in my head, but let's go ahead and just use the calculator. So 84.07 plus 5.04 plus 14.01 plus 48 plus 32.06. And we get 183.18. So I added all of these numbers. All of these numbers go to the second decimal place. So my answer needs to go to the second decimal place. So that's our molar mass of saccharin. We can use this molar mass just like we used the molar mass of carbon earlier. Okay, so if we want to look at how many grams of saccharin are in 8.5 moles, okay, we can use this value to do that. And feel free to pause the video and try it out on your own. So we're going to start with our 8.5 moles of our saccharin, so our C7H5NO3S. Set up a conversion factor. We want to go from moles to grams, C7H5NO3S. And we're going to use our molar mass from up here. So we have 183.18 grams of our saccharin per mole. Okay, remember whenever we have that unit down below, that means we have 1 of that unit. So I take my 8.5 times 183.18 and I get 1557 grams of C7H5NO3S. I have 2 sig figs in my starting, so I need 2 sig figs in my ending. So 2 ways to represent that. You have 1600 grams without a decimal, or you can do 1.6 times 10 to the 3. So either of those answers are correct. All right, go ahead and practice molar masses, practice calculating and using them as a conversion factor. And make sure you get to know a periodic table, okay? Because you're going to have to look up molar masses a lot, so you're going to want to kind of have a general idea of where all of these atoms are